This glowing orange ring is the event horizon of a supermassive black hole. It's a cosmic giant, similar to the one anchoring the center of our own Milky Way, packed with the mass of millions of suns. To reach this size, physics dictates a very specific, very slow timeline. A black hole begins as a small seed, the collapsed core of a dying star, and then spends billions of years slowly grazing on surrounding gas and dust. There is a strict cosmic speed limit on this growth, known as the Eddington limit. Think of a black hole like a funnel. If you pour material in too fast, the friction superheats the gas, generating an intense blast of radiation. That radiation pushes against the incoming material, meaning the black hole literally chokes itself if it tries to eat too quickly. Because this limit strictly throttles how fast a black hole can grow, creating a fully mature giant should take nearly the entire age of the universe. Finding one fully grown right after the Big Bang should be a physical impossibility. Then we launched the James Webb Space Telescope. By pointing its massive golden mirrors at the darkest edges of space, astronomers peered deep into the past, looking at the universe when it was just 600 million years old, a mere infant in cosmic time. In that ancient darkness, this image captured hundreds of mysterious glowing objects scattered across the background. Astronomers simply called them little red dots. Initially, researchers assumed these were typical early galaxies forming their first stars, but when they analyzed the specific light frequencies, the chemical barcode of the glowing gas, they found the unmistakable signature of gas spinning at millions of miles per hour. That extreme speed is the fingerprint of a supermassive black hole actively devouring material. We had stumbled upon a population of cosmic monsters thriving in a baby universe. They had somehow reached full maturity in a fraction of the time physics allows, challenging our existing models and earning them the title universe breakers. One of these ancient black holes was caught consuming gas at an astonishing 40 times the Eddington limit. It was tearing through material at a rate that should have choked it, completely ignoring the established laws regarding radiation pressure. As Webb continued to scan, it found an even deeper anomaly, a black hole weighing roughly 50 million times the mass of our Sun, sitting entirely alone in the void. Cosmology relies on a specific sequence. Gravity pulls gas together to form billions of stars, a galaxy. Only then, deep within the center of that massive stellar structure, does a black hole take root and grow. The house must be built before the resident moves in. This solitary giant possessed no surrounding galaxy. The resident had arrived before the house existed. This single observation reverses the established order of cosmic creation, suggesting black holes might actually be the gravitational anchors that later pull in the stars. If these early giants didn't slowly evolve from the husks of dead stars, we have to ask how they were born in the first place. The light seed theory says gas forms a star that dies, collapsing into a small black hole. Webb suggests heavy seeds, or direct collapse. A massive gas cloud crunches directly into a huge black hole, bypassing the star face. By skipping the stellar evolution step, these objects would be born massive from day one. This explains their quick growth and why a black hole could exist in an empty void without a single star around it. As researchers more thick blankets of cosmic dust, when the intense light from the feeding black hole pushes through that heavy dust, it scatters and stretches, creating an illusion that makes the object appear significantly heavier than it actually is. Factoring in this dust layer means these black holes are slightly smaller than our first estimates. But the illusion only explains the exaggerated weight. It completely fails to explain why hundreds of them were able to form so early, or how an orphaned black hole could predate its own stars. Even with the dust correction, the timeline of the early universe is still broken, leaving the greatest questions unanswered. Finding out our most trusted models are flawed can feel unsettling, but in astrophysics, a broken rule isn't a failure. It is the system working exactly as intended. Centuries ago, Isaac Newton wrote the absolute laws of gravity, and they worked perfectly, until they didn't. When Newton's calculations failed to predict the orbit of Mercury, it didn't destroy physics. It cleared the path for Albert Einstein to reveal a deeper layer of physics. These little red dots are the modern-day cracks in our current models. They prove that the early universe was wilder and more creative than we ever imagined. A moment of wonder. When we look into the dark and see our established laws of nature shatter, we shouldn't turn away. Every anomaly is an invitation to discard what we thought we knew, step through a new door, and discover the next profound truth of the universe.